Today I am going to discuss the yield stress, the relation of yield stress with the dislocation density. The yield stress is related to the dislocation density rho h sigma s equal to sigma naught plus alpha gb rho to the power 1 by 2. This is the relation between the yield stress of the material with its dislocation densities, where rho is the dislocation densities. As we all are aware of that, the dislocation is very important for the strengthening of a material. Dislocations act as an obstacles for the other dislocation motion, and when we hinder the motion of a dislocation, then the strength of the material increases. It means that all the strengthening mechanisms simply works on the fact that you have to hinder the motion of dislocations. Okay. You have to make the dislocation movement more difficult, and you can make it by putting a lot of dislocation in a materials, so the dislocations itself will act as a obstacle for the other dislocations, as though two dislocations simply repel each other. Okay. Sorry. So this is our yield stress. This sigma naught is the friction stress, and this is overall resistance of crystal lattice to dislocation motion. This alpha is a constant, and its value is 0.3 to 0.6. It varies from 0.3 to 0.6. This G is the shear modulus. Okay, shear modulus is just the ratio of shear stress to the shear strain, and also called the modulus of rigidity, and it just give an idea about how the material is rigid, how much material is rigid. For example, diamond is very rigid, and it's about 6 times more rigid than that of a steel, so its G value is approx 6 times that of steel. This B is Berger vector, and this rho is the dislocation density. So let's name it all. This is the dislocation density. This is the dislocation density. This is the friction stress. Friction stress. G is the shear modulus. Shear modulus. B is the Berger vector. And alpha is a constant, which values vary from 0.3 to 0.6. Okay. So we see that from this equation, as we increase the dislocation density, the yield stress of the material increases. And how the dislocation can be generated in a material? The basic concept behind this is that when we deform the material, okay, the dislocation is generated through the Frank-Reed source. And the Frank-Reed source, what is the Frank-Reed source? Every material contains some inclusions, and these inclusions act as a Frank-Reed source where the dislocation are generated. Okay. So as you increase the dislocation density, the yield stress of the material will increase. Okay. You can also say that if you increase the number of dislocation inside a material, then the dislocation themselves can be an obstacle for the other dislocation. And this is more like similar to imagining there is a huge crowd coming out of the movie theater. Okay, then one person will find himself an obstacle for the other person. So let's draw the graph between the yield stress and the dislocation density. So when we draw the graph between the yield stress and the dislocation densities, we can say that from the equation, this dislocation density is not, this is the square root of dislocation densities. Okay, So from the equation we can say that here there is a linear relationship between these two, and the graph will be a straight line, and the slope will be this much, alpha into GB with the slope, and this will be the intercept on y-axis. So let's draw the graph. This is sigma naught, this is sigma naught. The graph will be in a straight line, and the slope will be alpha GB. That is the slope, equal to alpha GB. Okay. So we can say that when we increase the dislocation densities from here to there, we are going to increase the dislocation density, the yield stress is going to increase. But when the dislocation is very, very low, I mean when the dislocation density approaches zero, then the stress tremendously increases, and it becomes equal to the theoretical cohesive stress goes up to theoretical cohesive stress. So when there will be no dislocation, not a single dislocation in the crystal, then the yield stress will be very, very high. And as the dislocation density approaches zero, then the yield stress will go up to theoretical cohesive stress. So this is very important in this graph. Okay. Now we have a simple question for you. You have to select the correct statement out of these four. The first is toughness and strength both can be increased by making grain size finer. The second option is any two dislocations have some minimum distance between them. Third option is for materials to be easily deformable, we should have maximum of 3 slip systems, and the twinning can occur more easily in HCP than slip. Okay. The fourth option is twinning is more easily be taking place in HCP crystal system than slip. Slip is more difficult to occur in HCP crystal system. Is it correct or not? You have to decide. Be prepared for the answer of these questions, and we'll discuss in next lecture. Thank you very much.